Hello everyone and welcome to another video where today I will be talking about dark matter. Now this video will be called something like why do we think dark matter exists and it's not just gravity working different. This video is not specifically addressed at flat earthers or science deniers or conspiracy theorists in general. It is addressed at anyone who has asked themselves that question before, but it was certainly caused by a discussion between Craig from FTFE and Jaron from Jaronism. I sometimes watch flat earth videos when I'm in the office, like on the side. I have them running in the background, and then if I stumble across something interesting, I thought I might have a look at it. So, what is it that has triggered, if you will, this video?
That's your model. Your model is the idea of dark matter and dark energy make up 97% of the universe. Hold on, make up 97% of the universe. You've never observed it, but you guys claim it must be there because you need it for your model to be correct. That's not science. That's not what you're supposed to do. You're supposed to throw away the theory. It's wrong and go back to the drawing board and find one that works.
But there isn't a theory about it.
And now, what Sharon has said here is not what is actually going on. It is a pretty misinformed picture about the whole dark matter, dark energy thing. Now, this video I will only be talking about dark matter because I am not very knowledgeable about dark energy, but I am a bit knowledgeable about dark matter. For those of you who don't know me, hi, I'm Olaf. I am currently doing my master's degree in physics and my master's degree in astronomy, two different master's degrees. And even though I don't do anything specific with dark matter, either on the fundamental side in particle physics or on the astronomical side with galaxies and the such, I do neither of those things. While studying the two subjects, you get a basic idea about both of these angles, and I would like to do a bit of an explanation for that. So this is what we will be doing today. So here we are back at my trusty old OneNote notebook. Right, so dark matter, first of all, why do we think that it's a thing? Why do we think it exists? And the second part will be, why do we think it's not just gravity working different? Because that's something that this will be astounding to some flat earthers. We have thought about very hard, and we came to the conclusion that that's just not it. Because flat earthers sometimes portray as if we just push dark matter out there to keep gravity alive, but it's really not that. We have thought about changing gravity. It's called modified gravity, and modified gravity fundamentally doesn't work. It does not work. It makes very weird assumptions, but we will be talking about all of that in a bit. Let's go for the observational evidence of dark matter. Now, this is by far not an extensive list, and is very, very much just scratching the surface, scratching the surface. And I will be, I chose these four things that I will be showing you because they are the more easier to understand. There are so many more that are pretty complicated, both on a more fundamental particle physics side and on a very astronomical side. But those I don't think would be that much helpful for laymen. So let's begin. First of all, rotation curves. What is a rotation curve? Imagine that you graph the distance from the center of a galaxy to the rotational velocity. So how fast is something spinning compared to how far it is away from the center, right? This is something that in astronomy we see that in astronomy and in nature we see all the time, right? Our planet turns around, but our planet is a solid, so that's what we expect. Solid body rotation, right? Or rigid body rotation, as it's sometimes called. But within our solar system, for example, we see Keplerian rotation. That comes from a central force and objects kind of rotating around the central force. And this is Keplerian. And so for a galaxy, the reasonable assumption would be that, well, in the center of the galaxy, there's a lot of gas, there's a lot of dust, so there will be some dragging going on that almost would look like as if it was a solid there. It's not solid there, but it's like the gas density there is so high that there will be some almost solid rotation in the center, and the further out you go, the thinner the gas and the dust become. We will turn rather to Keplerian orbits, right? So the green line here is what we would expect. This is the resulting curve, and is a reasonable first expectation for a galaxy rotation, right? So that's what we expect. However, when we look at the observations, we see this. It rises almost as we expect it to do, but then it stays up. Why does it stay up there? That doesn't make any sense. The expectation is that it drops down. Now, you do some calculations. They aren't exactly difficult, and you reach the conclusion that after some calculation, there is about 6 times more mass at the very outside of the galaxy than there is visible, that we can see inside, if you will, of the typical confines of a galaxy. This has been come to be known as a so-called dark matter halo, and we believe that every galaxy has something like it, or almost every galaxy has something like it, regardless if it's a spiral galaxy or an elliptical galaxy, a dwarf galaxy, and something like that. Alright, so here's a depiction of what those velocity, of what the rotation curves would actually look like, the velocity rotation curves. So if you have here again the distance, and here you have the velocity, you can see that they behave differently. This is what we would expect from just the light that we see in a galaxy, and this is what we see in reality. You can see that these behave very differently. And as we have figured out through calculations in the past couple of decades, this is possible if, and there is a second animation, it is on the dark matter side, I'm sorry, we have figured out that this is possible if there's dark matter at the outside of the galaxies. So that's just one piece, right? That's one piece. After some calculation, there has to be more mass outside of the galaxy. There is a theoretical second option that gravity works different on large scales than it does on not large scales. This would be weird because we wouldn't have seen that anywhere before in nature, and there isn't really an explanation for it within physics as of yet, and not even a working model for that, but you know, this is still on the table. Second thing is what's called the Varal Theorem. This is more of a mathematical thing, but it holds true for everything that rotates around a central force. It's called a conservative force field. For example, the solar system could be approximated very well as such a conservative force field. The sun as a central force, or like as kind of causing a central force with gravity, and everything else kind of moving in that conservative force field. Within that, and I'm heavily simplifying the Varal theorem here, you can say that twice the kinetic energy roughly should be minus the potential energy. Now mind you, here it says minus the potential energy because if one is positive, the other one has to have the opposite sign, because potential energy in this case with a central force is negative. It's just a mathematical thing. If one is positive, the other one has to be negative. You could say the absolute values have to be twice the kinetic energy should be roughly the absolute value of the potential energy. Well, this works extremely well for stellar systems as well for galaxies. It has absolutely no problems for the solar system. For the solar system, this is very spot on. But for some galaxies, especially galaxies that are in galaxy clusters, this doesn't work. Now, after some calculations, you reach the conclusion that either gravity works on different scales, mind you, not the same scales as the rotation curves, but other scales, or there is some non-visible matter somewhere in the galaxy. Now, this doesn't say where this matter should be, just from the Varal theorem. This one has said that it should be rather on the outside, right? Okay, now, third thing is gravitational lensing. When you have galaxy clusters and you have a light behind them, they bend the light particularly strong. Now, how do you determine the mass of a galaxy or even of a cluster? Well, this is a bit difficult. One of the things that you can do is called the mass to light ratio. If you get the light of a galaxy, like how the flux, how much luminosity there is that you get from a galaxy, it is reasonable to assume that you can have some conversion factor between the mass and the light, right? And we know of those conversion factors. We know for these for galaxies, we know about like star clumps of stars, right? Some arrangement of stars, groups, things like that. We know the mass to light ratio. But if you look at clusters, it just stops working randomly, kind of. clusters are a lot heavier than we would expect from the mass to light ratio. They bend the light more than we would expect from the mass to light ratio. This can be seen particularly well in the galaxy Abel 1689. This is not a year. This is a name of a galaxy. And if you do some calculation, well, it starts working out again if we use the dark matter that we have found earlier in the rotation curves. I sketched it here. This is a galaxy cluster where you have 3 galaxies. No, please note that galaxy clusters have more than 3 galaxies, but I didn't want to draw them. Without dark matter, the light is being bent not as strongly, but with dark matter, it is bent strongly, and the specific kind of dark matter is the one that we have already hypothesized at the rotation curves, right? So it still works. And clusters in general do interesting stuff. You have 3 major mass estimates. First of all is the lensing that we have talked about already. The third one is the velocity dispersion. This goes into the Varal Theorem again, a bit more in detail maybe. What we really measure is the velocity dispersion, which is the scatter in the radial velocities of the individual galaxies. And from that, you empirically, we got 2 relations. One of them is called the Tully-Fisher relation, which is for spiral galaxies, which says that the luminosity is proportional to the maximal radial velocity to the power of like 3.5 roughly. It varies a bit for which wavelengths you look at it. It's 3 to 4.2, I believe. And the second one is the Faber-Jackson relation. This is for elliptical galaxies, and this says that the luminosity is roughly proportional to the velocity dispersion to the power of 4. Again, it differs a bit depending on how bright the galaxies actually are, but the power of 4 is a reasonable middle ground, right? And from those, we get the luminosity approximations, and from the luminosity, we can get to the mass. And as I said earlier, these disagree from a certain scale of things with what we can see at smaller scales. So either gravity works different at different scales, again, not the same scales as before, or there's some matter that we can't see. The third one is, the third main mass estimate here is X-rays. X-rays in astronomy come almost only from hot gas, or heated gas, or something like that, or very young stars, but big stars, but the major component comes from hot gas. And from the flux of how much X-rays we get, and from the spectrum of the X-ray, we can calculate the gas density. And if we know how dense a gas summer is, we can get an idea of how strong the gravity has to be in that region for the gas to be that dense there. And from that we get a mass, right? And this mass, again, would tell us that clusters are heavier than what we calculate for them to be, but the galaxies on their own, if you look at a galaxy that's not inside a cluster, it's fine. So, mostly fine. Depends on the galaxy, I guess. So, again, either gravity works different at large scales, or there's mass that we can't see. And now, from this list alone, it would seem that there are really 2 possibilities that are more or less equal. But the problems with modified gravity are very big. Why do we think that it's not just gravity working different? First, all of the observations, not just the one I listed, there are many, many more. I just listed the 4 that I thought are the most accessible. All of the observations that we have are consistent with invisible mass. There is a plausible fundamental mechanism for it, from a more particle or size. The graviton is already hypothesized. We already, if it does indeed exist, we already have a certain idea of how it looks and things like that. It has to have a spin of 2, for example. And the fundamental mechanism is that there's just some sort of particle that we haven't found, that some fundamental constituent of nature that is just not interacting with the electromagnetic force. This is very possible. There are 4 fundamental forces: gravity, electromagnetics, the strong and weak nuclear force. And some particles just don't interact with one, right? So it is absolutely feasible that just dark matter doesn't interact with one of those. There are particles that don't interact with one of the others. Why can't dark matter not interact with the electromagnetic fundamental force? Absolutely possible. We have the plausible mechanisms all together. The particle physicists just have failed so far to provide evidence from a particle side for dark matter. But there are some hypotheses, and we're like at the very beginning of this journey, so it's not exactly surprising that we haven't found something yet, right? But now the weird thing about modified gravity. As we have talked already, it must change over large scales. Now, first of all, the scales are different depending on the observation. For some, it already changes how it behaves at the galaxy scale. For some of the observations, it has to change how it behaves at the scale of galaxy clusters and things like that. So this isn't really consistent. The second thing that is very weird, if you want to calculate the acceleration between two bodies, and I'm using Einstein's notation here, in the simplest case for the Schwarzschild metric with a stationary observer, because if I had written down Newton's equation of motion here, or Newton's equation for the force of gravity, I can already hear the flat earthers say, oh, but it's not Newtonian anymore, so I'm using Einstein's model, because, yeah, I'm not giving you that kind of satisfaction. So it must change over large scales. So for one scale, you would be able to calculate the acceleration with that, and if you move one of the objects further away, you suddenly can't anymore. And this is something that is very, very weird. And the worst thing, according to some new papers that came out 2 or 3 years ago, some observations to be thinkable with modified gravity, it would even have to push repulsive gravity. That is something that has never been seen in experiment and observation before. There is no known fundamental mechanism of how this would work from a purely fundamental particle, elementary particle size. Doesn't make sense, and this is a completely arbitrary change over very large scales. So first, gravity behaves normal out to some scales, out to the scales that we have tested it so far. Suddenly changes and makes attraction stronger or weaker depending on which observation you have and depending on the scale you have, and then at very, very large scales it becomes repulsive. This is just not the simplest explanation for it, because, for example, when you have the bullet cluster is a cluster that has very well-known kinetic movement, and so it can be used very well to test for things like that. And the movement of the bullet cluster, so far, can only and solely be explained with general relativity with dark matter. No modified gravity can explain it so far. No alternative model has offered any explanation for what's going on here. Gravity seems to still fundamentally behave as it is described in general relativity, and there's just some sort of mass that we cannot see. This is the conclusion that science has reached for the last couple of decades, and we are sticking with it because it works. Now, flat earthers think, or science deniers in general, not only flat earthers, I have heard other people say that, they say that dark matter doesn't work because it is just, or can't be real because we made it up to fix our model. Absolutely not. If someone was to come around today at our university, for example, and figure out that no, gravity actually works different, and here I can show calculations on how that is, and it makes sense for all of the things that we have talked about here and all of the other things that I haven't, and it makes predictions for other things, and those are then tested and remain true, this would be a guaranteed Nobel Prize. I can't emphasize how guaranteed this Nobel Prize would be. This would be one of the most secure Nobels in all of history. So I would love to find out what's behind it, if it's just gravity working different, but I don't think that this will happen anytime soon. Now, does this mean that it is 100% completely dark matter? No. Could be something else. We just haven't figured it out yet. All of the evidence so far points towards dark matter. And this is why the conclusion of this video is, well, it likely is dark matter then, isn't it? Alright, so with that, I think the video is done. I thank you very much for watching. If you did enjoy this video, maybe consider leaving a like. If you enjoyed it a lot, maybe considering subscribing. To all of the flat earthers that have watched it so far, first of all, thank you for making it this far. I hope this cleared up some of the misunderstandings that you had before, and you have now a better understanding of why we say, or why we think that dark matter is reasonable. Yeah, so with that, I will see you in the next video, and until then, have a nice time. Goodbye!